Good morning, good afternoon, good evening to you all. Welcome to our fourth of the faculty lecture series. We are super excited to be here today with Professor Jordan Suchow. For all of you, just some housekeeping before we begin. If you can hear me and you can hear me well, please type in the chat that you can hear. Otherwise, please let us know and we will try to assist you with your audio. Wonderful. Today's topic is going to be about AI entrepreneurship. Dr. Suchow is going to be talking to us about bootstrapping autonomous robotaxi services. Just a little bit about Dr. Suchow. He is our assistant professor at Stevens, our esteemed School of Business, I believe in the Business Analytics and AI program, correct?
That's right.
Wonderful, wonderful. Dr. Suchow received his PhD and his master's from Harvard in psychology and his bachelor's in computer science from Brandeis University. So, Dr. Suchow, without any further ado, please, the floor is yours.
Good morning, everybody. Stevens is located in Hoboken, New Jersey, right across the river from Manhattan. And when I started here as a faculty member in 2019, I pretty quickly realized that I was only walking distance from some of the federal courthouses in Lower Manhattan. And I have this kind of armchair interest in the law. And so I decided one morning to look up what was on the docket that day at the courthouse. And I was pretty interested to see that there was a case called SEC v. Elon Musk, case number 18CV8865. And interestingly, court proceedings like this are open to the public. One can just walk in and watch it happen. I knew Elon was going to be there, and so I thought, hey, why don't I go and take a visit? So I did. I went through security, sat down in the courtroom, and while we were all waiting for the proceedings to start, there was this reporter who happened to be sitting right next to me. And the reporter, as reporters do, started talking to me just to figure out, I told her, oh, I'm a professor at Stevens, interested in AI and machine learning and all that. And then she just asked me a very simple question, which is as follows. Do you think they can do it with cameras alone? Okay. We're going to unpack that question a bit. But in slightly longer form, what she was asking me is, do you think the company Tesla can create a fully autonomous level 4 or level 5 self-driving car using a strategy that is, unlike all the other players in this space, highly focused on vision via cameras integrated into the vehicle? So today we're not going to answer that question, but what we are going to do instead is to discuss a fundamental structural problem that gave rise to the need to ask that question in the first place. And that structural problem, which you might call the bootstrap conundrum, is one where most AI and machine learning systems are data intensive in the sense that they require substantial training data. And often the best data comes from actually deploying the system in the wild and seeing where it actually succeeds and fails. So what then do you do when you're creating a new product, perhaps even in a new product category as a startup, for example, where really the only way to collect exactly the data you want is to go and actually deploy the system to collect the training data. But then the only way to deploy the system is to actually have first trained it. So you get this kind of chicken and egg bootstrapping conundrum. Now, there are a bunch of possible solutions to this kind of bootstrap conundrum. How do you collect the data when you need the working system to actually collect the data in the first place? And let's talk about just a few of them. One solution that lots of folks go for is maybe you can license data from a vendor. In the case of robo-taxis, indeed, now in 2026, there are plenty of companies out there that are data vendors for autonomous vehicle systems, and that could help. A second option is perhaps you can generate your own data by dogfooding the product. It's very common when in the life of tech startups to start by having you be your own first user. And so it gives you the opportunity to deploy the product not at scale for your actual consumers, but just using it yourself. This might be using it in the context of your own vehicle driving around on test tracks. It could be if you're creating some kind of app. It could be you using the app in the process of even creating the app itself. Right? So it's generating data by you as the developer actually making use of the product. A third option might be to simulate data. This says, hey, maybe we can't launch the system in the wild, but maybe what we can do is to create some kind of virtual environment, some kind of simulated system where we can run the software that backs the system in a somewhat realistic environment. And in fact, in the case of autonomous vehicles, this is also another strategy that you see sometimes of many of the actual key systems that are doing the navigation are defined in software, and you can simulate a sensor environment much in the same way that you could simulate many other kinds of scenarios that are just expensive to run, like a space launch, for example. The next option is perhaps what you can do is to deploy the system in some kind of sandboxed or constrained environment. This is also an approach you see often with autonomous vehicles. This amounts to something like driving the car around on a test track or in some kind of environment where it's not actually the production system being integrated into, running on the public roadways, but running around a test track like M-Track is one example of that. And then the last option is perhaps just go for it. Just deploy the system, see what breaks, and go from there. Or, and this is what we're going to focus on, I want to talk about the pattern, the key pattern that underlies many of the most successful systems that solve that bootstrapping conundrum. And the pattern is as follows. Why don't we create some kind of hybrid human AI system that embodies a handoff of control back and forth between the two or more subsystems? Having that kind of handoff integrated into the architectural design of the system means that if you get it right, on day one, you can actually launch the product or the system because you have the human labor underlying the product that can actually do the task, do the driving, do whatever it is end to end. But you also have a on-ramp to a fully automated system. You have a mode of interpolating from people doing the work to machines doing the work. And we're going to look at this pattern in a few different contexts. We'll look at a few different designs. We'll look at it in the context of autonomous vehicles, where it's often called level 3 automation. We'll also look at it in a very different context, one of meeting scheduling, where it's not a named pattern, but just one of a more general hybrid human AI architecture, where there is a defined handoff of control between different systems, some human, some machine. So let's take a look at this in the context of autonomous navigation. The key architecture is dyadic. Dyadic meaning there's one person, one machine, and the control flow, the control handoff between the two is about as simple as it could possibly be. The person hands off control to the machine, which continues with full control of the system until there is some point of uncertainty, at which point it kicks back control to the person, who continues on from there until they decide that it is safe to hand control back to the autonomous system, and so forth. So you just get this loop, this kind of handoff back and forth from the person to the machine, to the person to the machine, to the person to the machine. Okay, that's the general pattern. Let's see how this actually plays out in the context of driving automation. The most famous framework for describing the levels of autonomy in driving is put out by SAE International in their Levels of Driving Automation framework. This framework has 6 levels. It's 0 indexed, so it goes up to level 5, but it starts at level 0. And I just want to orient you to these levels a little bit. The key level that we're going to want to talk about is level 3, but it'll help just to give you the endpoints and describe what is so special about level 3. Actually, when I like to talk about the levels of driving automation framework, I like to add and tack on a new level to the left, level -1, because level -1 is really easy to think about. It's just like what a car looked like in 1970, which is to say, very minimal automation features. It's you driving the car, and that's about the whole story. At the very other end of the spectrum, level 5, is the full dream of autonomous vehicles. This is the style of autonomous vehicle where you could hail an autonomous robo-taxi. It comes to your doorstep, you get in, tell it where you want to go, take a nap, and when you wake up, you're there. The point being that for level 5 automation, there is not only no expectation that the person sitting in the car will actually assume control of the vehicle. You could, at level 5 automation, go so far as to remove the steering column and just make it structurally impossible for anybody in the vehicle to actually control it. Right? It is full autonomy and is defined as such. One little wrinkle there is that there's level 4 and level 5, which are almost identical. The only thing that makes level 4 not level 5 is that there is some constraint placed on where or when the vehicle will operate. So the classic examples of this would be a geofence, that is to say, some kind of digitally defined boundary where the vehicle just won't drive outside of that boundary. Perhaps because the regulators haven't allowed you to, like, you might be able to test in the Phoenix metro area, but not in Nevada or not in LA. Or that boundary might be placed not as a geofenced location, but it might be some other kinds of conditions, like, for example, weather conditions. Maybe you don't drive in heavy fog or when it's raining very heavily. What I'll note is that many human drivers probably are level 4 autonomous, in the sense that, I think many of us actually don't feel comfortable driving in literally any place in the whole world. You can imagine some kind of situation where you're just like, I'm not sure that I'd feel really safe driving there, or under those conditions. And likewise, like, many of us pull over to the side of the road when it rains too hard, or would say, it's not a great time to take that trip. The weather just isn't right for it. There's too much snow on the road, right? And so, all that to say, level 4 automation is actually quite far in having solved the problem. And many companies would be quite happy if they had a functioning level 4 vehicle. That's well on your way to the dream of autonomy. Okay, so we're zeroing in on level 3. Let's now look at levels 0, 1, and 2. 0, 1, and 2 are driver support features. These are the kinds of features that you've likely seen in cars that maybe you own or have seen ads for, or have seen, or have had, taken a taxi and it might have had this feature, or maybe you've read some article and seen that, like, there's a new version of a vehicle that has this particular feature. These are not broadly available in all vehicles, but they're the kinds of things that we're regularly seeing in consumer vehicles, and just year over year, more and more of these automation features are being adopted. So that, for example, at level 0, you might get a blind spot warning. That's like somebody's driving in the lane to your left. When they're very far behind you, you can see them through the rear view mirror. As they drive up on your side, there's some point where you can't really see them unless you turn your head and look over your shoulder. And so this provides a mechanism for telling you, hey, there's somebody in your blind spot, often implemented as the car beeping, or there may be a light on the side view mirror. Right. So that's an example of a level 0 driver support feature. It's momentary warnings or assistance. Level 1 allows the system to assume control of either steering or brake and acceleration. So that would be, for example, lane centering, keeping you in the center of the lane, or adaptive cruise control, which is like a fancier cruise control where if the car in front of you stops, so too will your car, instead of traditional cruise control where if the car in front of you stops and you don't do nothing, you drive through them. And then level 2 is where you combine the two. You have both automated steering and brake, which is this gets you like lane centering and adaptive cruise control at the same time. It means you could go onto a highway, set this, and it'll just continue on safely until you need to get off at an exit, at which point you'd have to assume control. Okay, so now we've gotten at it from the left and at it from the right. And so how do we get then from level two, which is a system where at least momentarily it can assume control of the vehicle, but only in very limited conditions, like driving on a highway without making any turns or changing lanes or what have you. How can we get from there to level four, where it's the vehicle in control all the time? And the key bridge between the two is level three. It's a bridge. You can see that it's mostly colored green, but there's also some blue. And what's special about this is it is at level three that there is definitionally a handoff of control between the human driver and the automated system. Just to give some examples of how this is implemented, you might have a driver, so because there's going to be a handoff of control. The physical vehicle itself needs to have a steering column. There needs to be a driver sitting in the driver's seat. And often what will happen is the automated system is engaged. It drives and does continues on in the trip until there's some moment where there's some uncertainty in the system, and it reaches a level where it does not know how to safely handle a scenario, and it then kicks back control to the human driver, who needs to be sitting there, alert, ready to assume control at a moment's notice. The person assumes control, safely handles the situation, and then re-engages the feature to hand back control to the autonomous system. Okay, so what's so special about this is that it is tolerant to a wide range of capabilities of the autonomous system, right? You can imagine what happens if you have an autonomous system that just really isn't that sophisticated. One where it can handle a very limited range of scenarios, but in almost every other scenario, it faces high uncertainty and needs to kick back control. That's fine. What that looks like in practice is a person basically driving using a kind of adaptive cruise control where they're alert, they're the ones who feel in charge. Every so often they engage the autonomous system, but it just is kicking back control to them all the time. So it's mostly the person doing the driving, except for example on long stretches of highway where maybe the automated system is actually doing quite a lot of the driving. As the R&D process for the autonomous system gains capability, eventually you get to a point where that human driver is doing less and less of the work, right? And eventually the human driver is doing so little of the work that you effectively have a level 4 system. The only thing you're missing is the level of certainty that you need to be able to structurally change that interaction mode so that it is never kicking back, is structurally never kicking back control to the human driver, right? If you can have a level at the very top end of level 3, it looks very similar to level 4. It's just you still have a human driver sitting there ready. And so at some point, it becomes safe to simply remove the driver, and then bam, you have a level 4 system, right? And so that's what's so special about this level 3 system and why this pattern is useful in the context of solving that bootstrapping problem for startups and new ventures, creating these kinds of products where you have a clear vision of what full automation looks like, but you don't have the capabilities today. It provides a mode of interpolating between the human labor that you have that can do the task well and an autonomous system. And it means that on day one, you can actually launch some kind of product actually in the exact domain or environment that you want to do the testing. And that's key. Okay, so we're going to take a look at what it looks like to actually use this strategy in just a bit. But before we get there, I want to show you that this particular interaction pattern, this dyadic interaction pattern of a handoff of control from one human and one machine back and forth, is not the only hybrid human AI architecture that's possible. In fact, it's only one of them, and there's a very large design space of different kinds of interaction patterns. And to show you that, I want to show you one more architecture that's just one step up in terms of complexity. This workflow is one that backs an experimental product put out by Microsoft called Calendar.help. And it's in a very different domain than autonomous vehicles. It's in the context and was built in the context of uh, scheduling meetings. Okay, so scheduling meetings, you might think like, oh, why would we want a system to do that? And it's a problem that there's actually many startups that have tried tackling this. In part, it's just a very practical problem. Lots of people go to meetings and schedule meetings and need to schedule meetings. And it seems like the kind of task where, oh, if we had the right systems in place, we might be able to do this much more efficiently. And so let me just show you the vision that the creators had of what this might look like in Calendar.help. What you see here is an email client. The email is to Lizzie Contoso. It's from Gabriel. Gabriel writes to Lizzie, "Hi, Lizzie. I went over your resume and would like to schedule a call to go over the role. Cortana can help us find time next week to chat over Skype. Thanks." So this is a pretty common interaction, right? It's some kind of screening in an interview process. What I want you to note is that CC'd on this email is Cortana. And at the time that this was first developed, this was one of the early hybrid human AI architectures that was written about in the like HCI human computer interaction literature. Um, when this was written, people wouldn't have recognized the name Cortana per se. It would have just sounded like, oh, it's an interesting sounding name. I don't necessarily, it wouldn't have registered as a product of or like a product of Microsoft. And so the interface here is very simple. One simply CCs Cortana, just in the way that you might have CC'd some team member or administrative assistant or what have you to assist in scheduling the call. And the idea here is now that is the handoff. Gabriel has now handed off control of this workflow to Cortana, who will take it from there end to end, with the final result being that this particular meeting that Gabriel has requested will be scheduled. Um, in my classes, I have the room go through and unpack that as a task. It's the kind of thing that on the face of it seems quite simple, but actually scheduling a meeting is sometimes easy, but sometimes remarkably complex. Um, Folks have talked about the quote unquote jagged frontier of AI, where there are some tasks that are easy at the same time that there are other tasks that are quite hard for modern systems to do well. And I think meeting scheduling is exactly that kind of task, that kind of domain where there are some components of it that are quite easy and some components of it that are quite hard. Just to give you a taste of like one task that might be quite easy and one that might be quite hard. Um, Here it's pretty easy with 2026 tech to figure out um, who the hiring manager is in this particular context, right? Or to know what is the system, the software system that will be used to, host the video chat. It says, right there, Skype, and Gabriel's the one writing this email, and it's clear enough from that. In contrast, even a question that's only one step more complex, such as who ought to attend the meeting, wow, all of a sudden, this is significantly more difficult. We definitely know that there's two people who are going to be there. There's going to be Lizzie and Gabriel. But as to who else ought to attend this meeting, this depends on organizational context. It depends on who is expected to attend these kinds of screenings. For certain kinds of organizations and certain kinds of roles, the answer to that is it's a call between Gabriel and Lizzie, and that's that. In others, there might be many other considerations. It might be depending on the kind of role. It might involve having HR on the call, or having legal on the call, or having other kinds of other team members on the call. And sometimes just even making that judgment might require this kind of latent context that isn't necessarily obvious from just the plain text of the email. It might be implicit in the kind of social relationships between the team members or the organizational context, which the system may or may not have access to. Okay, so all that said, Scheduling meetings can sometimes be quite easy, but it can sometimes involve a wide variety of different subtasks. And let's take a look at what the folks who created Calendar.help said about how they went about solving this bootstrapping problem, this kind of conundrum where, clear vision of what they want to create. They know a person can do this task end to end. And in fact, they have people who are doing this task end to end currently in their organization. They also have some idea and some vision for how one might do it in an automated way. But how do you actually get that interpolation? How do you launch the system today in a way that allows you to interpolate from the human system and the vision of autonomy? Here we go. Calendar.help. We decided to go with the Wizard of Oz approach, but took it one step further. I'm just going to pause there for 1 second and give you 30 seconds on what the Wizard of Oz approach is. You might wonder, like, why are we talking about the Wizard of Oz all of a sudden? Wizard of Oz, originally there's a movie, there's a play. You might know it from Wicked. The Wizard of Oz himself is a character in the Wizard of Oz. The key thing to mention about the wizard is that effectively he is a person who is wearing a mask of a machine. He is pretending to be a machine, or at least allowing others to believe that he is a machine. That label, Wizard of Oz approach, was adopted by the human computer interaction community doing behavioral experiments with people, where they wanted to solve a similar kind of bootstrapping problem, which is they want to be able to test autonomous systems and technical capabilities of systems before those technical capabilities are realizable, in the sense of, say you wanted to test human interactions with a human-like chatbot, but you wanted to do that in the year 2000, not the year 2026. You might say, oh, we don't have any chatbot in the year 2000 that can actually approach human level reasoning capabilities in conversations. Let's just fake it. Let's hire a person who's going to pretend to be the machine and chat with the person. And now we can use that as an experimental procedure. So the Wizard of Oz approach is one where there's a person behind the machine pretending to be the machine. Okay, so all that said, we decided to go with the Wizard of Oz approach, but took it one step further. Here's how it worked. We invited a handful of people from a few companies to sign up for our system, which we later named Calendar.help. Then they simply added the virtual assistant to the CC line when sending meeting invitation emails. The longer term goal was that the AI-driven virtual assistant would take it from there, looking at schedules and creating calendar invites for optimal days and times. But at the outset, the virtual assistant was actually us, parsing every single invitation email, looking for optimal solutions, and scheduling meetings. Although this was a lot of work, with nearly 2 years of iterations, it allowed us to get a product into people's hands early so we could observe their behavior and iterate quickly. It also gave us a deeper understanding of the problem we were trying to solve and let us start evaluating which portions of the work could eventually be performed through AI. We were delivering accuracy and collecting excellent data that could potentially bootstrap an AI solution down the road. Okay, so just going back to this workflow diagram, under the hood of Cortana in the Calendar.help was actually a three-tiered system, a three-tiered architecture that handed off control between the various tiers in order to perform the task end to end. So incoming was some kind of request, like the email that you just saw from Gabriel. That request initiated a workflow, which was a defined business process for carrying out the task of scheduling a meeting. That workflow broke down from the macro task of scheduling a meeting into many micro tasks and a process that combines them. The interesting thing is that when you look at those micro tasks, you see that kind of jagged frontier. You might find certain micro tasks like determine what time the meeting ought to be, or create a new calendar event with the meeting, or send an email to a follow-up email that could be automatable using whatever today's technologies are. You might also find other micro tasks that, using whatever the technology of the time was not automatable and could only be performed by a person. So once you've broken down that macro task into micro tasks, tier one was all of those was all of those microtasks that could be performed by then current technology. Tier 2 was taking the tasks that couldn't be performed by then current technology and having a crowd worker perform them. A crowd worker being somebody who's recruited using online recruitment services to perform small one-off tasks, such as labeling an image, reading an email and determining what time the email ought to be, uh, correcting a draft of an email, etc. The kinds of work that don't necessarily require deep context or domain expertise to perform, but could be performed by a wide variety of people on one of these online platforms for sourcing this kind of work. Now, the hope is that by breaking down the macro task into micro tasks, farming out the micro tasks to people and machines, combining them back together, that you could just do that to get the result end to end and automate the system end to end. But what they built into the system was a kind of fallback, a tier 3, which is an expert, that is, for example, somebody well trained in scheduling meetings, who is capable of performing the task end to end under a wide variety of situations. And that serves as a fallback so that if the combination of tier 1 and tier 2 fail, the tier 3 worker completes the workflow end to end and produces the result. So this is now a slightly more complex architecture, and now it has 3 systems, not 2. And the control flow is a little more complex, but it serves the same purpose. You get the same output, which is that on day 1, you can launch the system. You can launch the system and be certain that no matter what happens, the task is going to get done. Because worst case scenario, none of the micro tasks work out. It falls back to the expert every single time, and the person just schedules the meeting. Right? That's kind of what the creators said that they did. They basically just did it themselves, and started basically having everything happen at tier 3. The nice thing, though, is that over time, as you improve the workflow, as you improve the capabilities of the automated systems for performing the microtasks, as you find all those edge cases and beef up your system so that they can handle them, uh, more and more often, you don't need tier 3, right? You don't need to kick things to tier 3. And so this provides a means of interpolating, just like level 3 automation. It provides a means of interpolating from a fully human workflow to a fully automated workflow and lets you launch on day 1, right? So this is another example of that pattern of solving that bootstrap conundrum. Okay. So we've now gone over 2 of these kinds of hybrid human AI architectures. The simplest dyadic one, slightly more complex 3-tiered one. There's a very big design space of how these systems might work. Okay, you could have in the top left, number 1, simple dyadic system, human machine back and forth. You could have triadic, 3 different entities. You could have a hub and spoke model where there's some kind of shared workspace and different agents, human and machine, are working on some shared kind of artifact. You could have a hierarchical structure that mimics that of organizations where some nodes are people and some nodes are machines. I think that's a very popular thing to start thinking about today, that many people are thinking about agentic AI and including agents as parts of hybrid human AI organizational structures. You can imagine certain kinds of pipelines that just pass information back and forth between people, but between a sequence of people and machines. You can imagine a kind of marketplace structure or a swarm structure, some kind of mixed network-like flat organizational structure, some kind of escalation ladder. There's a very large design space, and in the same way that folks have experimented with organizational structure for people-based organizations, so too have people been experimenting with a wide variety of different hybrid architectures with people and machines. And I think we're just going to see more and more of this in the future, more and more experimentation along these lines, trying to landing on new kinds of structures that emerge when you have increasingly capable autonomous systems working side by side with people. Okay, so great. Solved. We have the pattern in hand. Now we can ask the question of how long is this actually going to take? Because that makes all the difference. If I tell you, hey, I have some means of interpolating between a human system and a fully autonomous system, but it's going to take 2,000 years in order to actually ever get to autonomy, you might say, oh, this is basically fraud. This is basically Wizard of Oz approach, just having a person pretend to be a machine. This is AI washing. This is not actually using autonomy. This is just having people do labor, kind of ghost work, and paint a facade of a machine in front of them. In contrast, if I tell you, oh, 3 years in, we're going to have what it takes to make the transition, then you might call this an actual strategy. You might say, oh, this is the right way to go about interpolating, getting the data that you need on day one, having the system work in the actual environment it's going to be operating on day one, and a clear path towards autonomy. Okay, what's nice is that in the case of robo-taxis, in the case of autonomous navigation, we can actually quantitatively measure how long this is going to take. And the reason we can do that is because we get good data on exactly how frequently the autonomous system needs to kick back control to a person because the regulators require it. In particular, in the United States, driving is mostly regulated at the state level. That's why in the United States, when people get a driver's license, it's given to them by the state and has the name of the state on it. It's not given generally by the federal government. And so the regulators, which would be, for example, the state of California or the state of Arizona, they just have a requirement that says, if you want to test autonomous vehicles on public roadways, you need to report to us each time an autonomous system kicks back control to a person. You need to tell us how frequently is that actually happening. What that means is that one can then create a plot that looks like this. So just to orient you to this plot, first I'll tell you what the axes are, then I'll tell you what the points are. The horizontal axis, left to right, says how many miles is that company putting on their fleet per year. Okay. Which is to say, if you have one vehicle driving around, like you have one driver and one vehicle driving around full time, maybe you're putting several tens of thousands of miles on the vehicle. If you have all the way on the right, like 3 million miles per year, this is a small to moderate fleet of vehicles operating nearly full time, right? This might be having 25 people full time driving around a city each year. So it's quite a lot of road time. The vertical axis is the miles between disengagement. This is on a log axis. So 1K is 1,000 miles. That's like, just to orient you, like 100 miles, the point at the bottom is like an hour and a half of driving. So 1,000 miles is like a few days of driving. 10,000 miles is like the amount of miles that a person might put on a car if they're just like, somewhat regularly commuting in an entire year. And so at the bottom is like a disengagement every hour or so. At the top of the vertical axis is a disengagement every year or so. And now let's look at the actual plot. Each point here is a particular company in a particular year. And so you see, for example, all the way at the top right shows you in 2019, Waymo put 1.45 million miles on the road. And then it shows you that it's like every 13.2 thousand miles was a disengagement. Now, the thing that I really want you to take away from this is that there's a lawful relationship, and this is happening in a 5-year period, which was a very key point in the history of autonomous vehicles. This was before there were any commercial services widely deployed. And you can see that the more miles you put on the road, the better performance you're getting. So that you can actually estimate how long it would take and how much it would cost to actually collect the relevant data and to live at level 3 automation. You can calculate that it's going to cost you, and you don't get this directly from this figure, but there's a McKinsey report that I'll reference a little later that tried to estimate this just very roughly. If you want to create a robo-taxi service and use level 3 automation end to end, you're looking at something like 10 years and $1 billion. maybe in 2026 you could get that down to 5 years and $1 billion. Um, but you're putting a lot of miles on the road. So the trajectory is in the right direction, and that's continued. That trajectory has continued over the next 5 or 6 years. Um, but you're looking at a lot of time spent at level three, but some real promise that you'll get there. Okay, so let's now return to that key motivating question. Do you think they can do it with cameras alone? What it means is that if you want to actually create an autonomous vehicle, a robo-taxi fleet, you have a choice to make. Option one is that you're going to do this in the traditional level three automation way. This is what most of the companies in this space have done. It is classically what Waymo, I would call them the most successful company in this space, has done. And it's what many, many, many of their competitors have done. Step one is you lean on LiDAR. LiDAR stands for light detection and ranging. You send out a laser, get the light back. Um, you have a sensor that measures the time it takes for the light to return to the sensor. The nice thing is you know the speed of light in the medium that it's traveling in. And so if you know when you sent it, know when you got it back, know the speed of light, you can use that time to get back the distance. You've probably seen equipment like this, like surveying equipment, where you're basically using this as a very long ruler or measuring tape to just see like how long one point is from another. And indeed, most companies decided, even though these systems were pretty expensive back when they were making the initial decisions about strategy, to install LiDAR on the devices. This is an early example of the Waymo vehicle. It's a car that's retrofitted with LiDAR, which is to say they didn't manufacture the car from the ground up using LiDAR. Instead, they just added LiDAR onto the device. Once you've done that, you then pick a city. And the reason why you pick a city is because you saw that curve. You're going to need to put millions of miles on the road in a particular city in order to get there. And so you really only get to do this once. There are very few companies that can, like there are no startups that can just bankroll $1 billion of R&D. I mean, maybe in 2026, there's now 2 or 3 startups that have managed to get folks to bankroll $1 billion in R&D, like the hyperscalers and the frontier AI labs. But that's an anomaly. And in general, like this is the big bet that these companies had to make. So they basically all pick Phoenix and San Francisco in particular because those states, Arizona and California, have nice regulatory environments where they actually allow testing of robotaxis, and they're also just generally, particularly with Phoenix, easy-ish places to drive with reasonable weather. So it's a good place to make the bet. Next step, you do a decade of R&D and drive millions of miles on the road. And then here's the key thing, which is great. You've just spent $1 billion in 10 years driving in the Phoenix metro area. Now, what did you get out of that? If you're lucky, what you've gotten out of that is a autonomous vehicle that can operate in the Phoenix metro area. And when you now go to expand to the next city, it is significantly easier to do the second city than the first. That's your big bet, right? If it takes another 10 years and another $1 billion, it's game over. You'll never actually have a profitable service. But if it only takes 2 years and $100 million for city number two, and then even less for city number three, then maybe what you end up being is Waymo in 2026. This is an actual map up to date as of last night. They're currently operating in maybe 10 US cities, and they've got a list of maybe 20 coming up, including spreading internationally, testing in both London and Tokyo. Just over the past 6 months, I live in the greater New York City area, and I now see Waymos on the roads testing like very regularly, like basically all the time. They're actually on the roads doing this testing. I don't know how long it'll take. I don't know if they necessarily know how long it will take to do it. But the idea is it'll probably take less time than it did to do the Phoenix metro area, and so that's their path to winning this game of rolling out a robo-taxi service. Okay, option number two is you do what Tesla did. Tesla solves this problem in a very different way. They say, we're not going to go with LiDAR. Computer vision is at this inflection point where The capabilities are improving year over year. We think we can do this with cameras alone. Let's not actually install expensive LiDAR devices in our cars. Let's use lots of cheap cameras. Let's sell the car today with the promise. So there's many cameras on these devices. Let's sell the vehicles today with the promise of self-driving being just a year or two off in the future, and now use our customers as our means of collecting data. They'll be driving these cars on the road, not just in the Phoenix metro area, but all over. We'll collect the data that way, and then we will do our version of level 3 automation is not in testing, it's in having a particular feature, quote unquote, full self-driving, and we'll improve that capability over time to the point where eventually we can make that transition to full autonomy. Um, they're doing okay. I'll say that their predictions about that being a year or two off are perpetual. There's actually a Wikipedia article called The List of Predictions for Autonomous Tesla Vehicles by Elon Musk, starting in September 2013. That's like 13 years ago, if I'm doing my math right. And I'll just say, I don't have any Wikipedia articles about my incorrect forecasts. But on the other hand, they then do a decade of R&D, let your customers drive millions of miles on the roads from many cities all at once, and they've made a lot of progress. It still feels a year or two off. So by that mode, maybe they've made no progress. On the other hand, there really are lots of Tesla vehicles on the road with this full self-driving feature, which is not level 4, but is actually level 2 automation. But it's getting better and better every year. They're making real progress on the underlying problem. And if their bet is right, what they'll be able to do once they achieve a level of autonomy that they're comfortable with, they won't have to spend time rolling it out in the next city. They can roll it out everywhere at once. And so we're at a very interesting time where there's two different paths of companies that have tried to solve this bootstrapping problem in different ways. And we're like right in the meat of like uncertainty as to which of these is going to really pay off big. I guess is actually they'll probably both work. And I wouldn't be that surprised if in 5 years from today, uh, um, Waymo is operating in a couple hundred cities all over the world. And I wouldn't be surprised if in many places, Teslas can do, they'll still have steering columns, but can do a kind of level 4. They will be so high on the level 3 that people can just, that they may be approved to, have you take a nap in the car and it be okay. All right. The last thing I just want to say is there are folks who have been studying these kinds of timelines of autonomous vehicles. People always think it's just on the cusp and keep pushing back their estimates. So if you want to read more about this, there's a nice McKinsey report that they publish every year about the state of progress in this domain. And with all that, do I think they can do it with cameras alone? Um, I in principle, yes. In practice, we'll have to see. I think what we're seeing is that different places are operating on very different timelines. So what's most interesting is that in the context of the United States, there are 50 states and a few other jurisdictions, and mostly driving is regulated at the state level. So there's actually a nice database from the National Conference of State Legislatures that has put together this database of legislation on autonomous vehicles. And one of the key things you can see from that is different states have taken really different trajectories as to when they have started thinking about autonomous vehicles, when they created the right regulatory environment for testing. And I think that's actually a large part of the story as to why the Phoenix metro area won as the major hub of R&D for autonomous vehicles, with San Francisco being the like second. San Francisco gets that mostly because of having such a high density of people in the tech world, and also something about the regulators too. But the governor of Arizona, which is like super early on autonomous vehicles, created the right kind of regulatory environment, one where you can go to their DMV, their state autonomous vehicle testing department, basically, and fill out some forms and know who to talk to in order to actually get permission to test your vehicles on the road. And so, like, you have that. And then at the other end of the spectrum, you have folks advocating for a ban on autonomous vehicles in their state, right? And so that's one of the things that is kind of quite interesting, which is that there's no like global authority on driving. It's at a much more local level. And in that way, it's going to be quite heterogeneous in terms of what we actually see, where you'll see certain places, like even within the US, you'll see certain places like San Francisco and like Austin, Texas, and Phoenix, and a few other cities like really run with autonomous vehicles. And I wouldn't be surprised if in 5 years, like they're just all over the place in those cities. And then, but in 5 years, there will be other cities where it's just dead in the sense that like they might have even banned autonomous vehicles from driving on the roads. This depends on the industry. Some industries are regulated so that it's not their decision to make. So, for example, with robo-taxis, you don't get to just decide, hey, I want to go test my autonomous vehicle on the road. If one of us wanted to do that, we couldn't just, in our garage, build an autonomous vehicle and then, put it out there. There's a regulator. You have to convince them and you have to show them data. What kind of data do you show them? You show them like the disengagement reports. You show them plots, kind of like the one that I showed you. You show them that you provide quantitative measures of the risks associated with deploying your vehicle. There's actually, the regulators often require insurance on it, which means like you're providing quite a lot of quantitative data to various folks about the performance of your systems. In other domains, things are not nearly as regulated. Like maybe on the other end of the spectrum is like the ad tech industry, and there, it's really sometimes there are industry standards, but often it's up to the organization itself to think through these problems of responsible AI use and deployment. And there's lots written about this, but it's often quite particular to the specific application to define what are the criteria, what are the failure modes, how do we measure those, and where do we need to be in order to feel comfortable deploying the system. And this will be quite domain dependent. And I think, like some of the areas where there's the most interesting conversations about it are in healthcare, just also it being a highly regulated industry. And that's part of it's in those industries where there's the deepest thinking on these issues, in part because there really is a countervailing force asking you to demonstrate safety and effectiveness. So I think that very simplest pattern where you have an autonomous system that has a human fallback, that's a very common pattern. That might even be even simpler than the dyadic mode, right? Like the level 3 automation is a handoff back and forth and back and forth. I would say the most common approach is one where you have an autonomous system in the loop. It performs a certain task, except there's cases where it kicks control to a team. So one example of this might be in various areas of fraud prevention, where you might have a system that is um, making predictions about every transaction, but for the high risk transactions, flagging them for human review. And so that's an example where it's actually even simpler than dyadic. It's still one node, one human node, one machine node, but the control only ever goes in one direction, which is it starts with the autonomous system and then gets kicked back to the human. What I'll say is that I think we are now in the meat of time of, that's a weird analogy, but we are right in the heart of people experimenting with and exploring different kinds of hybrid architectures. I think a lot of people's imaginations have been sparked by seeing various demos of agentic AI. In particular, like if you've seen these systems like OpenClaw and its variants, which are basically act as like chatbots that you can integrate into many existing work environments, though please don't take that as a recommendation. It's like the absolute wild west of like security practices. So please don't take that as a recommendation. But just to say that like it's really sparked the popular imagination, and I think we're going to see a wide variety of different architectures explored, in part because there's a wide variety of different structures of teams and organizations, and people will just test what happens when we swap out this particular task, what happens when we swap in an automated system for that particular task in some larger process. That's a well-known pattern. The name of it is not coming to mind. If anybody remembers the name of it when I describe it, maybe you can write it in the chat or something like that. But um, there's this common pattern when you put some kind of guardrail or mechanism in place that and then it changes people's behavior in response to it. And so, yeah, that's a very common thing to see. And the overall safety of the system is not judged independent of the hybrid architecture's, you know, jointness. It is the full end-to-end hybrid architecture that is the thing being judged, right? When they track how often does the vehicle get into accidents, it's not simply a question of how often does the automated system um, fail. It's a question of what happens with the hybrid architecture. What happens when you have, a person who has wrongly come to rely on an automated system, and you often see very simple things like, you're supposed to be alert and ready to assume control at any moment, but people are like, oh, it's doing pretty well. I'm just going to start texting, right? And that's quite dangerous. It's very tempting, and that's actually one of the big failure modes of these systems. And it also creates a lot of backlash because when you have this hybrid system and the system fails, there's a question of who do you attribute the blame to, both in the legal sense, but really also in the kind of popular imagination and reputational sense, which is that, if an autonomous vehicle at level 3 gets into an accident, do you say, the person failed to maintain control and to adequately supervise the system, or does it have blowback for the organization more generally and kind of taint the public's perception of autonomous vehicles, even if that particular accident might not have been attributable solely to the autonomous system, but was because of this kind of um, lowering of the guard that was created by the system actually doing pretty well. Tesla indeed has recently deployed a small 5-6 car fleet of robo-taxis in Austin, Texas. Those vehicles are at level 4 automation. They're geofenced to the Austin area, but are autonomously operated otherwise. As for which risks of driving are mitigated by autonomous vehicles, it's all the things that get people into trouble when they drive. This could be anything from being distracted to explicitly texting while driving, drinking while driving, as well as some more subtle issues that happen during the actual task of driving. Like, for example, there might be a lack of visibility as to a car 2 or 3 cars down slamming on their brakes and predicting what exactly will happen, whereas the vehicle might be able to actually see a bit further beyond just the car in front of you. And so, there's a wide variety of different kinds of risks, many of them related to limitations of human attention, awareness, etc., that are mitigated by autonomous vehicles. There's quite a lot of work in China on developing autonomous vehicles, a broad ecosystem of companies in that space there. What I'll say is just that as far as what we're seeing in terms of the most largest scale deployment of autonomous vehicles today, that's with Waymo in the United States. But China's moving fast in this area, and so it's a little bit hard to know what things will look like, say, 5 years down the road. Likely it'll hit different cities and countries quite differently, where I would expect that in the US, autonomous vehicles will be dominated by the American companies, but in other places the story might be quite different. What do graduate students need to know to be able to perform the kind of microtask analysis that determines whether a piece of work is automatable? And I'll say that there's really two sides to this. One of them is understanding the domain pretty well. You need to be able to know what are the work practices and processes in a particular domain. What does it look like to do the work itself? And the second is to have a good knowledge of what's out there with respect to the kinds of tools and systems and models that can be leveraged to automate pieces of work. Right? It's only when you have both of those knowledges bases jointly can you actually put them together and figure out what is the right tool for each part of the job. I don't think any one of the architectures is most effective. And this is really a research question that is being actively pursued in a wide variety of different literatures in the behavioral and social sciences and the computational sciences, trying to understand what exactly is possible with respect to new kinds of teaming arrangements, new kinds of organizational structures. And I think we'll see quite a lot of development in this area over the next few years. Calendar.help indeed had a three-tier structure, and is that enough? Well, it really quite depends on the particular capabilities of automated systems in that particular domain. So, for example, there might be a particular task where we don't just have one class of model or system that can perform the task. We might have, for example, a fast but inaccurate system and a slow but accurate system. And then on the people side, there might be teams of people that are needed to perform a task. Or maybe it can be performed by one person alone or by a team, depending on the precision that's needed in the determination. And so in that way, the kind of three tiers is just one point in a design space, and lots of other arrangements are possible. Cameras and many sensor systems indeed can be affected by things like bad weather, fog, rain. The key is having an integrated view of the environment by fusing information from multiple sensors. Some of these are just quite difficult, right? There are certain conditions that just make visibility and sensing quite difficult in the extreme. I don't expect we're really ever going to have autonomous vehicles driving through tornadoes, but all of the systems, in fact, make use of multiple sensor types, so that it is very common, even for the vehicles that do have LiDAR, to also have cameras, to have acoustics, to have GPS, to have a variety of different sensors that can be put together, in addition to map data that might not be based upon sensor systems, but is from third-party vendors, and all integrated into a unified view of the environment. So that's the key trick. In terms of visual blind spots, most of the vehicles have sensor systems arranged in a 360 view so that they don't have the traditional blind spot that people have looking over their shoulder. Some of the devices like LiDAR are not fixed in position, so some LiDAR devices might be fixed pointing forward on the vehicle. Others of them basically rotate to try to get a 360 view, or at least a wider view. What happens when autonomous vehicles get into accidents is a big question. It's one that really sparks the popular imagination, and this will depend on exactly what the arrangement is. So, for example, if you might have a vehicle like a level 3 vehicle that is where it's possible to run it in some autonomous mode, but it was just driven by a person, in which case it makes sense that the driver would be responsible. But if we're talking about true autonomy, where you perhaps even remove the steering column from the vehicle, it's typically the operator of the vehicle, in the sense that the company operating the Robo-Taxi service or what have you, that's responsible for any accidents, and they usually obtain insurance explicitly and are required to by the regulator. So that's usually what happens there. Yes, if we're talking about autonomous vehicles that are level 4 or level 5, the kind where it is possible to remove the steering column and the occupant is not expected to operate the vehicle at any time, then it should be no problem to have somebody who has low vision, for example, to be the sole occupant of the vehicle. That should be no problem. For the question of whether somebody who's blind or has low vision might be able to operate a level 3 autonomous vehicle, that will depend on the particular visual capabilities of the person and whether, for example, they're able to safely drive a car. Many people with low vision are indeed able to safely drive a car under certain circumstances, and they too might be able to operate a level 3 autonomous vehicle, though I don't want to make any broad claims about that because it's going to be quite dependent on the individual and the vehicle and what's allowed in that particular state or jurisdiction. My children are 1.5 and 6 years old, so if we're talking about whether I'd let them go hop in a Robo-Taxi cab by themselves, probably not. But I don't think I would let them hop into a normal cab by themselves either. But as far as safety, like would I trust a Waymo vehicle with the life of me and my children? Yeah, they're actually quite safe. I've seen the numbers, and if you've ever been in a taxi cab driven by a person, I'm not sure which way the balance of fear ought to go. All right, thank you very much.